All right, ready to dive into quantum computing. You've been doing some fascinating research on this, and we've got a great academic intro to get us started, plus a research paper that hints at some really mind-blowing possibilities.
Yeah, and it all ties back to something you've probably heard of, Moore's Law. You know, the idea that computer power doubles about every 2 years.
Right, but from what I've been reading, it seems like we're hitting a wall with that.
Yeah, exactly. We're reaching the physical limits.
So, like, how much further can we really go with cramming more transistors onto a chip?
That's the thing. Transistors are getting close to the size of atoms. Like, we're literally hitting a wall with traditional electronics.
So are you saying that, like, our laptops are about to become obsolete?
Not quite, but it means we need some seriously new approaches if we want to keep pushing the boundaries of computing power.
Yeah.
And that's where quantum computing comes in.
Quantum computing. Okay, so harnessing the power of quantum mechanics.
Exactly. Utilizing those principles to potentially, like, sidestep those limitations we were talking about.
I gotta say, quantum mechanics always kind of makes my head spin. Like, isn't it basically the rule book for how the universe works at the tiniest level?
Exactly. And it's a rule book full of surprises, let me tell you. You see, quantum mechanics governs how particles like electrons and photons behave. And it's very different from the classical physics we see in everyday life.
Okay, so how do we go from these, like, mind-boggling quantum rules to actually building computers?
It all starts with this idea of a qubit. It's the basic unit of information in a quantum computer. Unlike a bit in, say, your laptop, which can be either 0 or 1, a qubit can be in a superposition.
Okay, superposition. I remember reading about that, but can you remind me what it is exactly?
Imagine a coin spinning in the air. Before it lands, it's not heads or tails. It's both possibilities at the same time. That's superposition, being in multiple states simultaneously.
Okay, got it. So the qubit is like this blurry, spinning coin holding both 0 and 1 at the same time.
Exactly. And now imagine we have two of these spinning coins. They're linked in a way that no matter how far apart they are, if one lands on heads, the other instantly lands on tails. That's entanglement.
Whoa. That's kind of spooky. Like, are they communicating faster than the speed of light or something?
Yeah, it is pretty weird. Even Einstein called it spooky action at a distance, but it's a real phenomenon.
Yeah.
And it's a key ingredient that makes quantum computing so powerful.
Okay, we have these qubits in superposition, entangled across space, but how do we actually control them to do calculations? Like, how do you program a quantum computer?
We use quantum gates. They're kind of similar to logic gates in classical computers, but they work on these quantum states instead of just bits. So instead of flipping bits from 0 to 1, quantum gates are like choreographing interactions between qubits.
So it's like composing a quantum symphony,
Yeah.
where each gate is a musical note and the qubits are the instruments.
Yeah, I like that. And the beauty of this quantum symphony is that it can tackle problems in a completely different way than classical computers ever could.
Okay, now we're getting to the really interesting part.
Mm.
How does this new kind of computation translate into real-world applications? Like, what can we actually do with this?
Well, the research paper you shared actually highlights one example, Shor's algorithm. It's specifically designed for factoring large numbers, which is a task that's super difficult for classical computers.
Factoring numbers, huh? That sounds kind of basic. Why is that such a big deal?
Well, it turns out a lot of our online security relies on the fact that it's really hard for classical computers to factor really large numbers. It's the foundation of most encryption we use today,
Yeah.
like for your online banking or even just sending secure emails.
Oh, so you're saying a quantum computer running this Shor's algorithm could, like, crack the codes that keep our digital world secure?
That is the potential.
Yeah.
It's a big reason why there's so much excitement around quantum computing, but also some concern. That same research paper actually suggests that the encryption methods we use today could become obsolete within a decade.
Wow, that's a little unsettling.
It is. But it also opens up a ton of opportunities. Now that we've got the basics down, let's move on and see how researchers are actually building these quantum computers and what other amazing things they might be capable of.
Yeah, this is definitely getting me hooked. Let's keep going. Okay, so building a machine that can actually harness these quantum phenomena sounds, well, kind of complicated.
Oh, it definitely is. I mean, just imagine. Building a machine that leverages the strangeness of the quantum world, it's a huge challenge.
And one of the things I kept coming across in my research was this issue of decoherence.
Right. Decoherence.
Can you explain what that is and why it's such a big hurdle for actually building these quantum computers?
Well, think of it this way. Imagine you're trying to build a computer out of, I don't know, soap bubbles. Like, the slightest disturbance could make the whole thing just collapse. That's kind of what we're dealing with here. Decoherence is when these qubits, they lose their delicate quantum states because of, interactions with the environment, like even tiny vibrations or stray electromagnetic fields can mess things up.
So keeping these qubits in their quantum state, maintaining that superposition and entanglement, it's like trying to balance a house of cards in a windstorm.
Yeah, that's a great analogy. And it's a major engineering challenge. One way researchers are tackling this is by creating these super isolated environments for the qubits. Like, some systems are actually cooled down to temperatures that are colder than outer space, and others are shielded from any external noise with these, elaborate setups.
So it's like a constant battle to protect these qubits from the noise of the classical world.
It really is. But even with all these precautions, decoherence is still a big problem. So researchers are also working on these really clever error correction techniques.
Error correction. Isn't that like something we already do with regular computers?
We do, but quantum error correction is, it's a whole different ballgame. See, in classical computing, we can just make copies of our data as a backup, right?
Yeah.
So if a bit gets flipped, no big deal, we have a spare.
Right.
But with qubits, not so simple. There's this fundamental principle in quantum mechanics called the no-cloning theorem. It basically means you can't just make a perfect copy of an unknown quantum state.
Ah, okay. So how do you correct errors if you can't make copies?
Well, quantum error correction, it involves this clever technique of encoding the information across multiple entangled qubits.
Interesting. So you spread out the information to protect it.
Exactly. It's like weaving a safety net, distributing the information so that it's more resilient to these errors.
Like building a backup system right into the computation itself.
Exactly. And it's a crucial step towards building fault-tolerant quantum computers, ones that can handle the errors that are bound to happen because of decoherence. That research paper you shared actually goes into some of the cutting-edge stuff they're doing in this area.
It's amazing all the ingenuity that goes into making this technology work.
It really is. It's a testament to how collaborative this field is. You have physicists, computer scientists, mathematicians, engineers, all working together to overcome these hurdles.
It's like the early days of aviation, right? When these pioneers were tinkering in their workshops trying to, defy gravity and get those planes off the ground.
I like that comparison. And just like aviation transformed the world, quantum computing has that same potential. But building these machines, that's just the first step. We also got to figure out how to program them, how to actually write the algorithms that will unlock their true power.
Okay, so now we're talking about the software side of quantum computing. That's got to be a whole different beast, right?
It is. It's where the real magic happens.
Okay, so we've covered the hardware, the qubits, these incredibly sensitive systems. But what about the software? How do you actually program a quantum computer?
Well, it's definitely not just a matter of tweaking the code we use for our laptops. Quantum algorithms, they're designed to leverage the principles of quantum mechanics, things like superposition and entanglement, to solve problems in a completely different way.
You mentioned earlier that I was interested in healthcare, and the research paper actually highlighted some potential applications in drug discovery, right? Can you tell me a little bit more about that?
Absolutely. So imagine, right, you're a researcher and you're trying to design a new drug for a specific disease. Well, you need to understand how that potential drug molecule will interact with, say, a protein in the body.
So simulating those interactions at the molecular level.
Exactly. And those simulations, they can get incredibly complex. Even with our most powerful computers today, it's incredibly difficult to model the behavior of even a few hundred atoms accurately.
Right, because it's just so much data to process.
It is. But quantum computers offer this potential shortcut because, they operate on the same principles as the molecules themselves, quantum mechanics.
So they can kind of speak the same language?
Yeah. In a way, yes. Quantum computers are just naturally much better at simulating quantum systems than classical computers. And that research paper you shared, it actually highlights some of the early progress they're making using quantum computers to simulate, the behavior of small molecules.
So potentially, instead of spending years in the lab synthesizing and testing countless variations of a molecule, researchers could use a quantum computer to quickly screen and identify the most promising candidates.
Exactly. It could completely revolutionize the drug discovery process. We could develop new treatments for diseases like cancer or Alzheimer's so much faster.
Wow, that would be incredible. What other types of problems are, well-suited for this quantum approach?
Well, another area where quantum algorithms have shown a lot of promise is optimization. problems.
Optimization. Okay, so what does that mean exactly?
Think about really complex logistics problems, like finding the most efficient routes for delivery trucks, or maybe optimizing the layout of a factory floor for maximum efficiency.
Right, problems that pop up in the real world all the time.
All the time.
Yeah.
And they can get really hard for classical computers to solve, especially as the number of variables grows. But quantum algorithms, they can explore this huge number of possible solutions simultaneously, potentially finding the best one way faster.
So it's almost like having a team of like super efficient problem solvers working in parallel.
Yeah, I like that analogy. And these applications of quantum optimization, they go way beyond just logistics, right? They could be used to design more efficient financial portfolios, to develop better machine learning algorithms, even to advance our understanding of materials science. It's pretty amazing.
It sounds like quantum algorithms have the potential to impact almost every field out there.
I think so, yeah. And as quantum computers keep getting more powerful, more reliable, we can expect to see just this explosion of new quantum algorithms that are tailored to all sorts of specific applications.
So this is a call to action for all those aspiring computer scientists out there. It sounds like the quantum software revolution is just getting started.
It really is. This field needs creative thinkers who can bridge that gap between quantum physics and computer science to develop the algorithms that will truly unlock the power of this technology.
Well, this has been a pretty incredible journey. We've gone from, the very basics of quantum mechanics all the way to these potentially world-changing applications. It's really giving me a whole new perspective on the future of computing.
It's been my pleasure. And remember, the quantum world, it's full of mystery and wonder. So keep exploring, keep asking questions, and who knows, maybe you'll be the one to discover the next big breakthrough in quantum algorithms.
Thanks for joining us on this deep dive into the world of quantum computing. It's been an amazing conversation. Until next time, keep exploring.